Hello, I am Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. Please subscribe. If you're a returning viewer, it is great to have you back. If you like the video, please give it a thumbs up and or share it with classmates, colleagues, or friends, or whoever else you think might benefit from watching. Nice to meet you. Let's go ahead and get started. So in this video, we will talk about doing a significance test for the slope of your regression line. Now this is very important because the outcome of this test will really tell you whether or not you have a viable regression model. It's one of the fundamental things about linear regression. So I'll try to keep it simple, keep it visual, and so you can understand what's actually going on in regression. So let's go ahead and get started. So this video is brought to you by the great people at the Great Courses Plus. You are here because you either need to or want to learn something. And there are a few better places to learn things than the Great Courses Plus, where you can get access to over 10,000 different video lectures across many topics ranging from philosophy to math. So please look at the description below, click on the link, and help support not only my channel, but the Great Courses Plus. So let's go ahead and get to this video about testing the significance of the regression slope. So let's reset the table a bit because we're getting into things in regression that are a bit more, I won't say advanced, but they're a little bit more in the nuances of regression to that point where you really start understanding it at a deeper level. So let's reset the table a bit. So number one, how much variance in the dependent variable is explained by the model or the independent variable? So the whole point of regression is develop a model where we have the independent variable along the x-axis, and then we're going to try to make a reasonable prediction about the y value or the dependent variable on the y-axis. So the previous example we've been using is about the value of a meal at a restaurant and then whatever tip the server gets for performing that service. And usually it's about 15% is kind of what the average is. But we want to be able to use the model to make some predictions about other values. That's only going to work if there actually is a linear relationship between the two variables. I mean, that's kind of a basic tenet of regression. And then how good our prediction can be will be based off other things. So how much variance in the dependent variable is explained by the model or the independent variable. So for this, we look at the value of r squared or adjusted r squared. You've probably seen these in regression output, but it's a way to easily represent how much variation is actually explained by the model. So number two, does a statistically significant linear relationship exist between the independent and dependent variables? If there isn't one, then regression is no good. That's sort of the underlying point of regression, is that first you kind of have to establish that there is a linear relationship between the two variables. So is the overall F test or T test significant? Now in simple regression, these are actually the same thing. Okay, so the T test output you see in the software, whatever it is, and the F test are actually the same thing in simple linear regression. So that's one way we can look. And can we reject the null hypothesis that the slope of the regression line, so b sub 1, is 0? So think about that. If there is no linear relationship between the two variables, we're probably going to have a slope of 0. So you can think of a scatter plot where the data points are just randomly scattered everywhere. The slope is probably going to be 0 because there really is no correlation there. And actually in a video I did previously, we talked about the relationship between the slope and the actual correlation. Okay, so if you're interested in that, look at the previous video. Does the confidence interval for the slope contain 0? So remember that everything in regression, when we're using sample data, is an estimate. So they're going to have confidence intervals around them. Does that confidence interval contain 0? If it does, then we kind of have a problem because we're not exactly sure if the variables are linear related. So there are estimators everywhere, kind of like I was saying before. So Linear regression contains many estimators. B1, B sub 1, the slope of the regression line. B sub 0, the intercept of the regression line on the y-axis. The centroid, that's the point that is the intersection of the mean of each variable, so x bar, y bar. The mean value, y hat star, which we'll get to all this in a minute, for any value of x star. Okay, so that's an x that we want to find the value of y for, basically, okay, is what we're saying. We're talking about the mean value for any value of x. Then there's the individual value of y for x. That's a prediction interval. Two different things. That's going to be the next two videos, confidence intervals and prediction intervals. So one estimator is the mean value of y. The other one is an individual value of y. Two different things, but those are both estimators. And many others about variance and other things, okay? So there are estimators everywhere, and we kind of have to understand them to know what's going on. So here's the data we've been using. I'm not going to go into it. I've used this on several previous videos in regression. So we have bill amount and tip amount. It's just a scatter plot of those two variables. This is the regression model that we get when we perform the analysis. So y equals 0.1462x minus 0.8188. There's a slight difference in those two regression equations because of rounding in each individual software, but they're pretty close to being the same thing. So of course our slope is 0.1462. That's our b sub 1, slope of the line. Our intercept is down here on the left. We don't worry about that too much in this example. The centroid of our data is 74 and 10. That's the mean of each variable. And we interpret this as meaning for every $1 increase in the meal bill, we would expect or predict an increase in the tip amount of 0.15. That's basically how we would interpret this. Now remember that when we really want to fully understand regression, that this is a very simplistic explanation of what we get, but that's kind of what we're getting at, okay? So here is the output. So when we go ahead and we run this in a software package, we're going to get some output, of course. We have an R square of 0.749. The adjusted is a little bit lower because it's more conservative. Our root mean square error, or our standard error, same thing, is 2.74. That's a measure of how well the points fit around a regression model. Then we have the mean and the observations. The mean y, which is $10, and the observations are 6. So here we actually have our, what I call the ANOVA table. So we have all of our sum of squares, total sum of squares, model sum of squares, error, mean square, and the F ratio. And then of course our statistical test for the model, which in this case is 0.0259. That is significant because we usually have a threshold of 0.05. And then we have some more. And here we have our terms, our estimates, and things like that. And this is kind of where we're getting at in this video. So what we're looking at is this total bill coefficient down here. So remember that the slope of our regression line is 0.1462. That's the estimate there in total bill. That's all that is. That's where we get a regression equation from. We have a standard error. So remember, standard error is another way of saying sort of the variance of that estimate. Everything here is an estimate. So for the slope of the regression line, 0.1462 is an estimate of the slope of the regression line in the whole population. So therefore we have an error around it, or some variance around it. That's the standard error. And then we have our t ratio, which is our test that we're going to get to here in a few minutes. And then the probability that tells us whether or not it's significant, so on and so forth. What I want to point out here is that you'll notice that the ANOVA table up here in the middle, and then the t-test here on the bottom, they have the same values. So 0.0259, it's the same in each one because in simple regression, they are the same thing. So here's a regression equation. Again, we get that from our estimates of our coefficients. So 0.1462 is the estimate of the slope of the regression line, and then we have the intercept there minus 0.8202 and so forth. We kind of round up. So that's where we get that from. So where does this all mean? Especially this part down here in the red at the bottom. So standard error of the estimate, we saw that. So the standard error of the estimate, okay, is just, or the standard error is the standard deviation of the error term. We talked about that actually in the previous video talking about error. So the mean square error is just the square root of the MSE. So this is kind of a review from the last video. So the standard error is just SSC divided by n minus 2, which in this case is 6 minus 2, or 4. Then when we do that, we get a little bit of algebra, 2.742. And we're going to need this to actually do the confidence interval and the t-test and things for the slope. Okay, so that's why we're doing this right now, just kind of reviewing it. So the standard error is 2.742, and that actually is on the output that we saw earlier. So we have the SSC is here. Again, just kind of reviewing. The MSC is here. And then the standard error or root mean square error is number 3. Okay, so 1, 2, and 3. I just want to point out where each one appears on the output, because we will need them when we do the calculation here in a second. So now let's get to the meat of this video, and that's the confidence interval for the slope. And here is what the confidence interval looks like. Now, if you remember from way back when in basic, in the first few chapters of stats, you remember confidence intervals for the mean. So when we have a population out there and we take a sample, we're going to get a sample mean. But remember, it's just a sample. So there's going to be an error around that, or a confidence interval. And we'll say something that, like, we are 95% confident that the actual mean for the population falls within this interval. Okay? This is the exact same thing. So instead of b sub 1 like we have here, in that case we'd have x bar, plus or minus margin of error. Okay? This is the exact same thing. So b sub 1 is the point estimator of the slope. We know what that is. This on the right-hand side, plus or minus, is the margin of error, like any other confidence interval. So t sub alpha over 2 is the t value that we get actually from like the back of the book or wherever else we're doing in Excel or online, whatever. And then the s b sub 1 is the standard deviation of the slope. So the standard deviation of the slope. But the overall format of the interval is the exact same as a confidence interval for the mean. Okay, just a little bit different. So we have a point estimator, the t value here, and then the standard deviation. Same basic format. Now the thing is, we know 2 of these already. So the one thing we don't know is the standard deviation of the slope, s b sub 1. I guess that's how you'd say that. And the formula is s, which is the root mean square error. We saw that in the output, divided by the square root of each x value minus its mean squared. So we've actually done this in a previous video, but we can show how that works. So using our tips data from before, we can see that the bill, which is the x value, okay, which is the first column, that's x sub I. The average bill was $74. That's x bar over here on the left. We find the difference. That's obviously the subtraction sign. We square the difference, and then we get the sum. So that's everything under the square root sign. Okay, that's how you would figure that out. It's very simple. We put that back in, and then we have 2.742. That's the root mean square error. That's actually from our output there at the top. Okay, it was underneath the r square, adjusted r square. I think it was the third one. So 2.472 divided by the square root of 4206, which we just found out. We do that, and that is our standard deviation of the slope, which is 0.04228. And guess what? We've seen that before. Remember? It actually is in our output. So when we actually had that output there, next to the estimate for the intercept, which is 0.1462, we have the standard error of that estimate, which is 0.04228, and we just calculated that by hand over here on the left using a few cells in Excel, the piece of output we already had, and then we went ahead and did the simple algebra, and there it is. So we confirmed that the standard deviation of the slope, or the standard error, is 0.04228. So there you can see both. So what about the confidence interval for the slope? Now we have everything we need. So we have the point estimator for the slope, which came from our regression line. We have the standard deviation of the slope we just did in the previous slide, that SB sub 1. And now we need the t value to go ahead and finish our confidence interval, the margin of error. And that's easy because it just comes from the back of your stats book, or you can do it in Excel, I guess, or online. It's the t distribution with 4 degrees of freedom. So we find that, and it's 2.776. Now we just do some math. Very easy. So put everything in, do the multiplication on the right, then we can do the plus and the minus, the addition and subtraction, and now we have our confidence interval for the slope. So what we can say, if you look over here on the right-hand side, again, from the output, we can see that the lower 95% confidence interval in the output is 0.0288309. If you look over here on the left, we have 0.02885, and that's simply because of rounding, okay, but they're the same thing. Then we have the upper 95% of the confidence interval, or the upper limit of the confidence interval, is 0.26360, and so forth. Look over here on the calculation, 0.2636, the exact same thing. So again, we did the kind of by hand way of doing it, and we confirmed that to the output that we got actually using the software. Slight differences again due to some rounding, 5 digits out, but it's the same thing. And then the standard beta, if you remember from a previous video we did, the standardized beta looks pretty much the exact same as the correlation of these two variables because it is the same thing. Also, because we standardized the values in our previous video, we did the regression on standardized values. The correlation was 0.866. You round it up, and there that standardized beta appears there. So if you watched the previous video on standardized values, I just want to point out that, yes, that is the case, and here's where it is. So what are we saying with this interval? Like any other confidence interval, this is how we interpret it. We are 95% confident that the interval of 0.02885 to 0.2636 contains the true slope of the regression line. Same thing we would say in the confidence interval for a mean. So we're 95% confident that the actual population slope, if we did regression, lies within this interval. And that's how we interpret it. Question. Very important question. Does the interval contain 0? Does this interval contain the value of 0? No, it does not. So what we can do is reject the null hypothesis that the slope is 0. So remember in regression, we have our null hypothesis, that is that beta sub 1 is 0, or the alternative hypothesis is beta sub 1 is not 0. So we would reject the null hypothesis and say there's evidence that says that the slope of the regression line is not 0 based on this 95% confidence interval. So last thing about the t-test for significance. If you notice in the output, there's a t-test down there. Again, this is very straightforward. So here are our hypothesis for the slope of the regression line. So the null hypothesis is that the slope of the regression line is 0, and therefore no significant linear relationship exists between these two variables. So the test statistic is very straightforward. T equals b sub 1, that's the slope of our regression line, divided by the standard error or the standard deviation of our regression line, which we already found out. So we go ahead and just do some division, and we come out to a t statistic or a t value of 3.4584. And again, we have seen this before. It's in the output on the t ratio in the output, 3.46. Over here, 3.4584, round that up. That is the same thing. And we can confirm that they do match. One we did by hand, one we did by the software. So to figure this out, we just compare our t value versus the critical value, based on the back of the book or whatever else that you have. And actually we found this out, remember, when we did the actual confidence interval. So it was 2.776, remember, when we did our confidence interval, same thing. Our t value is 3.4584. Since our t value is outside of 2.776, it's beyond that value, we can say that our test statistic is significant. And again, that's why our p value in the output is like 0.25 or something like that. So actually, is it in here? Yeah, 0.0259. So you can see where everything comes together. We have the estimate of our slope under total bill estimate, the standard error we found, which is 0.04228. We can see that in the denominator up there. We can see that our t ratio of 3.46, that's the same thing we got up above it. our probability of 0.0259. Again, that comes from a t-table in the back of a stats textbook. We see that our interval for the slope, 0.288 and 0.2636 are the same we found out before, that we found out by hand. And the standardized beta, again, is just the correlation of these two variables based on standardized values. So everything we've shown in the output and by hand match. But the important thing I wanted you to get from this video is, one, where does it all come from? Where do all these numbers come from, and what are they trying to tell me? Okay, and then actually proving that the math matches the software. Conclusion. So does the confidence interval for the slope, b sub 1, contain the value of 0? In this case, it does not. That's the first question you should look at. Number 2, is the test statistic, t, greater than the critical value for t at the chosen significance level, in this case 0.05 because we're looking at 95%, incorrect degrees of freedom, which in this case was n-2 or 4 degrees of freedom. That's a fancy way of saying you look at your degrees of freedom, go to the back of the book or wherever else, you look at your t-table, find that critical value, look at your t-statistic, and then compare the two. That's all that is. This video is brought to you by the Great Courses Plus, where you can get unlimited access to over 10,000 different video lectures taught by award-winning professors from the Ivy League and other top schools around the world. You can learn about anything that interests you: science, literature, and yes, statistics, like this lecture from Professor Michael Starbird called Real Estate, Accounting for Value, from his course, Meaning from Data, Statistics Made Clear. And right now, the Great Courses Plus is offering my viewers a free trial and is also now optimized for Australia and the UK. So go to thegreatcoursesplus.com/Brandon Foltz, my name, to have access to the 10,000 video lecture library, or click on the link in the description below. Okay, so that wraps up this video about the significance test and confidence intervals for the slope of a regression line and where it all comes from, visually speaking, and from the software and the math, so you can understand where everything fits together. So I hope you found this a bit more insightful in the understanding a bit more of the specifics of regression. I think it's really cool knowing where this stuff comes from instead of just like a robot pulling the numbers out of the software. So I hope you found it helpful and interesting. Thank you for watching, and I look forward to seeing you again in our next video.